Okay, let me start with a reminder of what I said in the previous video. According to the divergence theorem, if you have a surface and that encloses some region in space, then the flux through that surface of a vector field, which in general is this, can be computed instead using a triple integral of the divergence of the vector field over this enclosed region in space. And remember that the divergence was simply the sum of the partial derivatives of the components of the vector field with respect to the corresponding coordinate. So the first component is differentiated with respect to the first coordinate, second component with respect to the second coordinate, third component with respect to the third coordinate. And so as a nice example, I thought that we could do the flux problem that I had done before, but now applying the divergence theorem. So if you remember, this flux problem was consisted of a cylinder and I had computed the flux before through this cylinder by breaking it into three pieces, like the top, bottom, and the cylindrical part. It's important here that you include both the top and the bottom, because if you don't include them, then the cylinder is not really enclosing anything, right? You need to, in order to apply the divergence theorem, you need to use a closed surface. And so, according to the divergence theorem, the flux would just be the triple integral of the divergence of the vector field. Now the divergence is easy to compute. That's a good thing about this theorem. It's way more friendlier than Stokes' theorem. So the partial with respect to x gives you 4xy, plus the partial with respect to y, which is minus 2y, plus the partial with respect to z, which is axz. And in order to do this triple integral, if you like, you can use cylindrical coordinates with the same as before, with x being x, y being r cosine of theta, and z being r sine of theta. So if you do this, now notice that this is a triple integral. So it would be the bounds go like this: 0 to 2 pi, 0 to 3, 0 to 2, and then remember that in cylindrical coordinates the differential of volume is dc or r dz dr d theta, but now x is playing the role of z, so the differential of volume in cylindrical coordinates now is r dx dr d theta. So and now what you need to do is just replace this in terms of their cylindrical versions. So this becomes 4x r cosine of theta minus 2r cosine of theta plus 8x r sine of theta. And all of this is being integrated times r dx dr d theta. So if you integrate first the things with x, you get the integral from 0 to 2 pi. Well, okay. There's a trick that you can do. Really, there's nothing preventing you from integrating first with respect to theta. You'll see why I want to do that in a moment. So I just want to switch the order in which I would have normally integrated this. The point is that if you integrate first with respect to theta, you're evaluating like you're integrating like cosine or cosine or sine from 0 to 2 pi, and each of those has integral 0. So in the end you get 0. So this tells you in a very straightforward way that the flux had to be 0, which we had computed by checking individually that each of the flux along each of the 3 surfaces was 0. There's another way, so what I'm saying is that this is 0. There's another way in which you could use the divergence theorem, which is, remember that this flux was really the flux along the top part, the bottom part, and the cylindrical part. So, say for example, these were very easy to compute, but if you remember the video, what we did last time, a couple of videos ago, this was sort of tedious, but you can use the divergence theorem like this, in the sense that instead of doing this flux directly, you could have computed a triple integral and then subtracted the 2 fluxes from the top and bottom. And in this case, you would also have found 0 minus 0 minus 0, and then you get 0. So this is like a quick way to see that the flux along the cylindrical piece had to be 0 as well.